Okay. Now we are switching gears, and in the rest of the lecture, it will be somewhere between philosophy and math and computer science. Okay. So I have to tell you a 45-minute summary of a long story called decision theory. And one part that I will skip is the hypothesis testing part, because I don't want to get into talking p-values with people and whatnot. There is enough discussion about it. It's important. I'll point out at least the parts in our textbook that it's good for you to read, but it's more like general culture purposes. If you would be really serious about hypothesis testing, that would take maybe 2 months. So you're not going to be able to do it. And if you're not very serious about it, it becomes very funky. There is even like a paper published by American Statistical Association on not so much meaning of p-values. Okay, people try to hack p-values and then try to sell their product. It's a complicated story that I prefer not to get into in this class. But I'll point out references for you, the short one in our textbook and a longer one from a very good textbook. That's all for hypothesis testing. This is the part I'm not talking at all. Okay, so what's decision theory? Let's go slow. You got some data, and we are talking about binary classification. Okay, is the picture malignant or benign? Is it cancer or not? Is it good or bad? Whatever. Talking about binary. Okay, and you want a predictor map F going from data to prediction. For every data, it predicts a label, 0 or 1. And then you got a loss function, which means, let's say I predicted 0, the correct label was 0, then I'm good. I predicted 0, correct label was 1, then what's my loss? Loss will depend on your application. If the correct label was 1, and if you predicted 0, you're not giving a positive when it was positive. And for some applications, it's fine. For some of them, if the positive was a ransomware, it's pretty bad. So loss will be defined by you depending on your application, right? And then the risk function is the risk of your predictor. What you do, you take this loss prediction, checked against the label, put your loss function on it, compute your expected loss. That's the risk of your predictor. That's what people would call risk function, okay? Now you're gonna, let's say, for a moment, you know a lot, you can create whatever predictor function you could. What would be your best bet? And the best bet turns out the following guy. Okay, why did I, let me put the correct thing here. Okay. The best bet turns out to be the following predictor. You got your data point X, you're gonna predict 1 or 0, okay? Suppose you know everything, right? Then the best predictor turns out, you can prove this mathematically, you're gonna go predict 1 if probability of label being 1 conditioned on the data you have seen is bigger than probability of label being 0 conditioned on the data you have seen times this quantity. And this is the loss 1, 0, loss 0, 0, This is depending on your loss function definition. As soon as you define your loss function, this is a number that you can compute. And if you know these probabilities, you know the best predictor possible. This is an old result in decision theory. Of course, we don't know all those probabilities in practice. That's why it's not terribly useful. But it's good to bring you some perspective. Okay, that will be the best bet if you would know everything. This, I don't know who proved this, maybe 100 years old. And I was doing the proof myself, but I'm not going to do it now. But I'll give you a small exercise. Now, let's do some quick Bayesian stuff, bias rule. Label being something, conditioned on data being something. Why did I? Give me a sec. There's some mistake in this writing. Yeah, so let me correct this. This shouldn't be 1, it should be a little y. Okay, fine. Label being an estimate, 1 or 0, when you know what your data is, can be written the same way as density of your probability distribution on your data world on that particular point. Usually, your distribution on data world is a continuous thing, could be discrete too. That's why I'm using densities there and probabilities for your label, because label is 0 or 1. It's kind of a discrete thing. Okay. So you could do your Bayes law, and this is equal to that thing. And then using that Bayes law, you can actually simplify your life in this complicated expression that came out from the optimal estimator. Okay. So what is it about? Probability of being 1 conditioned on your data should be bigger than probability of being 0 conditioned on your data times a number. I literally care about this divided by that. And it should be bigger than a threshold. That's what I care about. Okay. So you can write that ratio using this Bayes stuff like this as well. Probability of your data being X in terms of density when label was known to be 1 times probability of label being 1. And this should be at least easier to know. It's like I got a whole bunch of labeled data. What portion is 1? What portion is 0? It's a literally counting problem. So this should be okay, hopefully. This is for now just math. Right? You can write this guy also like this. And that's usually something people would do without telling. And now, turns out, for the moment, since I care about this ratio, and since this two stuff is given by my labels, I essentially care about this ratio here. And that's what you would see quite often. Okay, they would say this is LX likelihood ratio when data is label, when label is 1, what's the density of seeing the data I have seen, divided by when label is 0, conditioned on it, what's the density of seeing the data I have seen. That's like likelihood ratio. Okay, and then you'll start talking about tests based off of likelihood ratio, because the best predictor we just see in that math is just talking about this ratio and saying it should be bigger than something. And that something was given by your loss function definition. So your best predictor is a likelihood ratio. And it's kind of crazy, actually. You know, you could do whatever you want with prediction, and the simple thing turns out to be the best option. The proof is not hard, but conceptually it's a bit strange. You could do a complicated predictor. Turns out this would be the best, all right? Fine. So likelihood ratio tests will be just like this. You define this likelihood ratio, and you pick a threshold. If it is bigger than that threshold, you say 1. If it is less than that, you say 0. And the best predictor picks this threshold in the best way, okay? Overall, it's up to you to pick whatever threshold you like. This will be a likelihood ratio test. Very good. And then the best one is this. If you translate the theorem, best tau turns out to be this one. Okay. We usually don't know this best stuff, but at least it's useful to know the best predictor is something simple, just a likelihood ratio predictor for binary classification, at least. So far, so good. Any questions? We will get to stuff that you will see in modern machine learning talks soon. Even though this stuff feels like philosophy, it still gets connected to state-of-the-art words you will hear in the talks very soon. Okay, so far so good. So bear with me, all right? Not my fault. It's better to tell you this stuff than not. Okay, very good. And now a common scenario is like, if you hit the right prediction, no loss. And if you did something wrong, say same loss. And in that case, this optimal thing gets even more simplified. It's literally the ratio of the probabilities. Okay. And this would be given to you again if you would do MLE on this setting. Okay, MLE would, yeah, go ahead. Depends on your label ratio, you don't know. So let's say you're dealing with radiology data, hopefully not half of the people are cancer, you know. So
you care the same amount about like both
So this is, yeah, if this is your loss function. So loss function definition is up to you based on your application. The problem is binary classification. But as I said, sometimes this could be infinity if you don't want any false positive at all. So it's up to you to define, depending on your problem. Yeah. All right. Now, types of errors. So this is our prediction. This is the true label. If you got 0, 0, true negative, false positive, false negative, true positive. I hope this table makes sense to everybody. It's kind of, intuitive English. Just look at this part. I'll read over the rest. Does this part make sense to everyone? Let me wait. Owen says yes. Jordan, does this 4 stuff? They're good? Good, bad? Okay. All right. Now, true positive rate would be abbreviated as TPR. What is it? When you know label is 1, that means you're here. You can be false negative or true positive. True positive rate is true positive divided by summation of the 2. Okay, the rate of this divided by the sum of the 2. You could also write this as follows. Probability of your prediction being 1, conditioned on the label being 1. This is true positive rate. And it has a whole bunch of other names. Okay, it is also called recall. That will be the most common thing you will hear. Instead of true positive rate, people will say recall. And apparently, they also say power, sensitivity, probability of detection. Okay. That's the first word that you will commonly hear to be used. Second one is false negative rate. To me, these words make the most sense. True positive, true positive, false positive. But instead of that, you will hear a whole bunch of other words. And you don't have to remember all those, but if you need, you have this reference recorded for you. Okay, you can always look up. And I'll point out this reference in the Canvas as well. For this particular discussion, I think this particular book I'm using for the lecture is a little better exposition, so I'll point it out. It's an open source book. All right. And then what else you would hear very often? I hear this like type 2 error, type 1 error, but I always forget which one was that. So you'll probably hear those two. Okay. Now, what you will see to kind of assess the quality of a prediction, you would hear this precision quite often. What does that mean? Your guess was 1. Based on it, what's the probability of the thing actually being 1? The precision of your guess, basically. Okay. And if you follow through the definitions, this goes by true positive rate times this thing being actually 1, false positive rate, this thing being 0, divided by that. You don't have to be able to do this math on top of your head. That's not necessary, but you can also think about precision in terms of true positive and false positive rates. That's the punchline. Okay. And then you would hear this thing called F1 score. Again, I always forget the definition. I have to look it up when people use it. But what it means is the harmonic mean of precision and recall. And recall was this true positive rate guy. Okay. Yeah, that you need to be very careful. But yes, Jordan, go ahead. It's false positive rate. Yeah. Sorry, precision. Let me not say something wrong. I think precision is defined right here. The precision is you guessed 1. Then what is the probability of this thing being actually 1? So if you guessed 1 and if it is 1, then that's a true positive. Okay. If you guessed 1 and it's not 1, that's a false positive. So literally, true positive times the thing being 1 divided by true positive, the thing being 1 plus false positive, the thing being 0. Okay, that's the precision. So if you would have guessed 0, that's the other way around. As soon as you define precision, you can define the rest as well. Okay, so overall theme is as soon as you know true positive and false positive rate, everything else follows. You just look up the definition and then you see what it is. But these things historically developed by different communities, and then they all combine now. That's why we have so many words. Okay. So yeah, very good. Good question. So just look up here. This is your true positive. What is false negative? 1 minus true positive. Okay. Okay, so these things are all defined by each other. That's what I was trying to say. So you can use these words too in the definition. That will be fine. But the usual convention is go by true positive rate and false positive rate. And we will see something called ROC curves soon. That's where they are used as well. Okay, so far so good. Main point is, yeah, apparently I wrote what I was saying. As long as you know true positive and false positive rate, you know all these measures of accuracy. Pretty good. Then now the question becomes the following. Let's say fix some false positive rate. Let's say 1/3, a half, whatever. Then mess with your predictor, which has that false positive rate. Think about all the predictors that has that false positive rate. Try to maximize the true positive among them. What would you get out of it? Okay. And that's literally what this famous thing ROC curve is. They will plot here false positive rate. Let's say this was my alpha. And the thing here on top will be the maximum possible true positive rate for this particular false positive rate. Okay. And if you plot it, it will give you a curve that's called ROC curve, receptor operating something. Okay, I always forget what this stands for, but you will hear ROC curve a lot in machine learning talks. And this is what it is, okay? So you plot false positive rate versus the best possible true positive rate. That's an ROC curve. Sometimes people will abuse this word. They will just plot some false positive and true positive rates. They will call it ROC curve. There will be some curve below this. This is plotting the best. They would have some predictor, and they'll plot what they got. That's not the best predictor. This will give you a curve below this one. Okay. The official definition is this: you plot the best. Sometimes people will come and show you some ROC curve, and that might be curve of their own predictor, not the best one. Okay, so beware. But this is the official definition. Okay, now, yeah, go ahead. Yes, loss function. Very good question. Loss function should be agreed upon before we talk about true positive or no. Give me a sec. I'm taking it back. Does the true positive or false positive involve any loss function at all? I don't think so. Very good question, Jen. Here are the definitions. As you see, there is no loss function here. Loss function comes in when you try to find the best one. Best one will depend on your loss function. But true positive, true negative is very simple definition. The truth was 0, I predicted 1. The truth was 0, I predicted 0. Okay, just right here. The best possible, what I mean is this. Let me repeat that. Very good. So here, what I mean is this. Fix a false positive rate. Think about all predictors that have that false positive rate. Which one will have the maximum true positive rate, because that's what you want to maximize. That one will be the best. So you keep plotting the best rates. That will give you a curve. That's what's called an ROC curve. Any predictor you could come up with.
And that depends
on your design of the predictor. You could do whatever you want. It's very funny that you could come up with any result in this generality, but you can come up with stuff. So you could do any neural net you want. You could do any function approximation you want. Just give me a result that predicts labels.
that's possible.
Very good. That's a theorem I showed about 10 minutes ago. No problem. So I will put the link on Canvas as well. Yes, go ahead. So the line is when they're equal. This is like the diagonal. So the curve, very good question. So curve will have several properties. First, it will start from 0, 0, and it will end with 1, 1. Okay, this is like the guy who is always telling this is always lying, something like that. And the curve will always go above that diagonal, and it will be a concave curve. And this could be proved using the definitions. Now, your question is, I think, a better one. You're saying, okay, when I see this curve, what do I get out of it? Yeah, right. That's like, what do I get out of this curve? So if you really see the curve, then you know the best rate possible. And if your predictor is not far from that, you know you have a good one, for example. That's one implication. And now people get confused on this question. Like, I see a curve, what do I do about it? Now, one thing they did, I'll so so sometimes they don't plot the best one. They plot the curve they get out of their own predictor. Then you will get a curve below what I defined, because since it's the best possible, it's literally telling you the limits of what you can do. And then people would use, but this is a very good discussion, because it's not like a straightforward interpretation after this, but you will see these things used all the time still, even though there's no straightforward interpretation. So that's why I'm bringing this lecture today, basically, to have this discussion. Okay, one thing that you would pretty common see is this thing called AUC. It means literally area under the curve. You plot this ROC curve, and it's got some area under. You look at that area, okay? And then people would say, the more area I have is the better. And that's not always true. I'll tell you why they say that. I'll give you an example, okay? But here's an example. You will see two curves. They have the same area under, but their interpretations are rather different. Let's try to go through this. So it says, if you look at the false positive rate less than 10%, like somewhere here, okay? So this guy can have true positive rate like 80%. Meanwhile, this guy will probably cut off like somewhere here, 50%. So if this is your true positive rate. But if they only look at the area under these two curves, they look exactly the same. So that is a common summary used. AUC, yes, correct. Where is it going down? So it's going up, then going almost straight. It can go down too. As long as it's concave, it's fine. We don't know, it's never going to go down. There is no such thing. Well, let me think about a little more. That's a very good question. Okay, but here my main point was, if somebody just throws this AUC at you and says, my AUC is better, I'm better, that's something you need to be skeptical about. And it's, I think, a very good example to show that. Okay, so now let me at least show you why people would use this area under the curve. Here's an example. So this is called needle in a haystack example. What is it? So we got, suppose the probability of seeing your data X conditioned on label 0 is very small. It is like a Gaussian centered at 0. Are you able to read? Is it big enough? I can zoom in. Are you guys able to read? Okay. So when you know the label is 0, probability of seeing the X you have seen is very small. It's like a Gaussian centered at 0. That's going to be always a small number. So that means it's like your needle, okay? This X. And then if the label is 1, then you get a Gaussian on a positive scalar S. That's called the signal. If the label is 1, you got a signal, okay? Nice. And then you could work out the optimal predictor, and then, work out the true positive and false positive rates for the optimal predictor guy. And then you could plot, okay? And the answer, as you see, depends on, let me go slow here. So you compute all the stuff. You don't need to do all these computations. When you look at the answer, it depends on the signal divided by this gamma. This gamma is considered to be the noise. When you got 0, you would like to say there is no way that is my needle. But that doesn't happen. You get something close to 0. This variance is called the noise. Okay. And this number, S, is supposed to be like a big number. It gives you a signal that you found what you're looking for. And the false positive and true positive rates comes out as formulas given by this signal noise ratio. Okay. So that's literally what matters here, signal versus noise. And then now, as you mess with signal versus noise ratios, and if you plot the ROC curves, this is how they look. Let's try to look at it. So this purple guy is like signal noise ratio is kind of high. So your signal is strong. So you get a much better ROC curve. As your signal noise ratio goes down, you see the ROC curve is going down. And people will look at this. How do I know this ROC curve is going down? Well, the area under is also getting smaller. That's why, like intuitively, they would say area is more is the better. Okay, then that's why you will hear this AUC used all the time. Area under your ROC curve. All right, that's basic vocabulary of this language. But as I try to convince you, this area under the curve is not always a great measure of success. So if it is used as the only metric, be careful. All right. Yes. Yeah, it's right here. So suppose your false positive rate is less than 10%, which is that one here. When you look, this guy goes true positive at most like that 5 or so. This one goes till like that 8. This blue curve, if your false positive rate is small, is much better than the red one. Yeah. Questions? All right. So very good. So far, I'm introducing you the language that is used all over the place. What we talked about is like false positive, true positive, precision, recall, F1 score, and then we went on this ROC curves. Then I also tried to tell you this area under the curve notion. So far, that's about it. We also talked about best predictor early on, etc. Okay, now I'll try to tell you some other general facts. These are all facts, and they are usually not prescriptive. Like, you know this fact and you really know what to do. They are usually not that precise. And being very precise is hard on certain instances. So they give you a perspective, but you have to be filling the rest yourself. So suppose I got some estimator for my parameter. And we define the variance of estimator this way, expectation of squared minus that is the definition of variance. Now, what does variance mean? How different outputs you could get out of your prediction process. You're trying to estimate the exact same thing. If variance is big, you could get a lot of different answers from your predictor. That's what it means, okay? And now I want to know how much variance I'm going to get. And here the expectation is, you need to ask me, like, what is the probability I'm taking expectation over? Since we are just doing theory here, suppose you know like nature's distribution, in the sense that if you would know the density, you're using probability of nature, which means your application, that you're going to see your data, okay? You're not fitting like a model like Gaussian or whatnot. Suppose we know true probability here. That's good enough for discussion, okay? And then there's a theorem called Kramer-Rao theorem. It goes like this. You got, say, n samples from your nature's distribution. Basically, some application, real life, gives you these samples. And then you create some estimator based off of them. You plug in the data to your predictor. It gives you some estimation, okay? And suppose this is unbiased in the sense that if I would have like so much data in expectation, this will spit out the correct thing, okay? Fine. Then with this many data points, What do I know about the variance? We know it's going to be always bigger than equal to 1 over some information quantity. And that information quantity, called Fisher information, is defined as follows: number of data points you got times expectation of second derivative of nature's distribution. So whatever this is, if you have any estimate on this, that gives you a clear boundary on how good you can do. So the only point I'm trying to deliver here is there will be variance, and there's a precise mathematical lower bound you could know on it, which is this theorem called Kramer-Rao theorem. Okay, so you need to expect some variance on your prediction machine. Okay, I'm gonna get a variance, so what do I do about it? So this is usually called bias variance trade-off. You'll hear this thrown around again all the time. So what does that mean? Here, suppose this is like the true answer to your estimation problem. Write down the expectation of squared error, what you're guessing minus the truth, square it, take expectation of it. And you do a whole bunch of math, and you end up getting this. This is equals to the variance we defined plus the best thing your scheme can do minus the truth. That is called bias squared. So at the end, suppose my model is like a 2D plane here. I'm trying to predict a 3D thing. What's the best thing you could do? Put that 3D thing projected on your plane. That's going to be your best bet based on the machinery you created. So that's the bias of your prediction system. Okay? And then there will be some variance because your system will not always spit out the best thing. It will since you're doing something probabilistic, it will spit out some potentially other stuff, which is within the plane you created. And variance plus bias squared gives you the mean squared error, the expected error squared. Okay? Then now people would say, maybe I could create something biased to reduce some variance. Or maybe I don't want to be so biased, then I should expect a bigger variance, something like that. So they'll always talk about this variance versus bias trade-off. That's what it means. So one other way to look at it is like, suppose you created a very small prediction scheme, then the variance will be small because you have few choices. But then the thing you're able to express is just small, so likely you'll get a huge bias compared to where you're supposed to go. So this will show up all over the place, and it will come when we talk about generalization soon. Okay. Very good question. Does this capture overfitting? It's hard to give a clear answer, but I will tell you what is known. Let me see. So overfitting is about this, essentially. Before reading this, just listen what I will say, then we will go through it together. So Adam asked about, does this capture overfitting? What is overfitting? You train a model through some training data. It's doing super good on your training data. Then you take some data the model has not seen before. You give it to your model, it spits out nonsense. Okay, that's called overfitting. You fit so much to your data, training data, it is not generalizing to some data that it has not seen before. So overfitting means there is a big generalization gap. Now let me define that generalization gap more precisely. So this is your samples. Again, let's go by this supervised learning type of setup. This is your samples. And suppose these are like true labels to them. And then my empirical risk of my predictor is what was predicting versus the true label. Put your loss function on top. Sum your loss. That's your empirical risk, right? Or sometimes people might do an average, and they might also add like a 1 over n here to make it look like an average risk. So far, so good. This is the risk I'm estimating based on my data so far. I got my data points, and I predicted using my machinery. I compared against the label. I'm in supervised setting. I compute my loss. I sum it up, and I divide by 1 over n to make it reasonable. That's my empirical risk of my function, okay? What is the true risk? If you remember the definition, true risk is if I would take expectation over all possible input, the data that the model has not seen before, compute through all of them, that's the true risk. Okay, very good. And now, among your function family, there will be a candidate, F star, that is minimizing this empirical risk. Literally, you trained your neural net with this data. It spit out something that's supposed to be the best it can with the data it has seen so far. Okay? Okay. And the function family is all functions that your scheme can express. If you're using a neural net, think about all the weights you could put. It will be a different function now. And think about all of those functions as a function family. You keep training through data, and you're trying to find the best weights. What you're doing is you're trying to minimize empirical risk. You're trying to find this guy among your family that is minimizing this risk, okay? But the true risk is like expectation of loss over all data, not only the samples you have seen so far. Now, what is the generalization gap? It is the difference between the true risk versus your empirical risk. Or in other words, the true risk is empirical risk plus generalization gap. So now all our training schemes attacks on this one. When you test it on some other data, this will kick in. And what do we know about this one? Okay, that's the generalization gap. So if this is huge, we end up saying my model does not generalize. It's giving me nonsense when I test it on some data it has not seen before. And now Adam was asking about overfitting, underfitting. So far, so good. Any questions? I couldn't hear. Could you say again? Okay, fantastic. So the traditional view of generalization was this. I'll keep training. My empirical risk will go down. But if I fit it too much, the risk after some point will start increasing, which means it's not generalizing. And we would call this overfitting. And before that, we will call it underfitting. And you would see these U-shaped curves people throw at you all the time. But the empirical experience, what people have seen using this stuff, suggests it is not as simple as that. Okay. So for example, sometimes you would see a double descent. You'll like go like this, and you would think you're like overfitting. But after some point, it will start decreasing again. Okay. Or sometimes it will actually go like this. Think about this billion parameter models. What could be more overfitting than that? Okay, they ate all the data on internet. Do they do well? They do well. Okay. Yes, go ahead. Test.
No test versus reality.
Risk is related to, sorry, blue line is training error. This is empirical risk. Red is, you can think about test error. Okay. And what I was saying is like the traditional view is the first picture. This underfitting, overfitting narrative. You would always see a U-shaped curve. After some point, you're overfitting, you should stop there, etc. Right? And that actually shows up in a lot of places. This is not total nonsense. It has some truth in it. However, a lot of experience taught people that it is not always as simple as that. Sometimes you get something like this, you start thinking you're like overfitting, but after some point it starts decreasing again and it gets pretty well. And sometimes it goes fine too. Like theoretically, it is still kind of a mystery to explain the success of these over-parameterized models. Why do we see the success we are seeing by the scaling? It literally feels like a brute force to a computer scientist. We are trained to come up with clever algorithms. Scaling feels like brute force. Put it on top of each other. Yes, go ahead, Jordan. There you go. So Jordan is saying if you be even more fine-grained, like all this over-parameterized stuff seems to be doing fine, but some of them is doing better than the other. We're also having a hard time explaining why one of them is doing better than the other. That's even more finer grained than what I'm just trying to talk about. It's like you don't really see the overfitting in this gigantic billion parameter models. So the truth is a little more complicated than the traditional view. So then what can we say about this? So here's a fun experiment. So the experiment is this. Okay, so this is mostly for fun. But this is actually a done experiment with this inception model that was famous at some point. So what do? They take the training data with true labels. They train the model, okay? And then this is the training loss. This is the test loss, okay? Very good. And then what do? In the first case, you train it with true data and true labels. And then in the second case, you keep the data, then you randomly shuffle the labels. The labels are total nonsense. Data is the same data, okay? And then in the empirical risk part, the optimization goes very well in both of them. The model fits the nonsense labels or good sense labels as well, that's fine. But in the generalization part, when you're using the true labels, it does much better than the false. Okay. This is an experiment. I'll give you the link to this book. So the point is like, we are training true data, and that's all we do. And that only attacks the empirical risk minimization. It doesn't tell you too much actually about the generalization part, which we actually cared. Okay. Even if we would sit down and do the math and really understand the training process, which we don't have it for the moment. We use stochastic gradient descent or whatever. We will talk about optimization algorithms in this class. We are not able to analyze them in the type of optimization that goes into all kinds of machine learning. We're able to analyze it only for nice functions like convex and whatnot. And suppose we managed to do it. We analyzed optimization processes we use for gigantic neural nets. Great. You still don't really have any idea about the generalization part. Okay. So the truth is a little complicated. Okay, now can we say anything at all? Can we bound the generalization gap? So this is kind of the heart of what's called statistical learning theory. Okay, don't read what I wrote there, I'll get there. Like people were thinking about this already in 70s and 80s. And when they were only thinking about, say, perceptron or very simple algorithms, the question was like, I got some hypotheses, which is my prediction. Or I have a collection of hypotheses, which I will try to pick the best one through data. What is the best I could do? What can I prove about my generalization error? Since then, people have been working on this. Somehow, these things have forgotten a little bit in mainstream machine learning. But since I love theoretical computer science, TCS people never let you forget this. So I'll tell you what is known a little bit. So first, we have again a function class. This is all possible functions we could create in our prediction scheme. Okay. Then this is our data. This is true data and true label. Let's put them together. Let's call it Z. And I have a loss function that I agreed. You put your predictor compared against the correct label, put your loss. Let's call it H. And I would like this thing to be not so crazy. Like if I gave it two similar data, I would like a similar performance. Okay. If this thing is too crazy, it's very hard to prove anything about it. So we need to assume for what I'm going to show you, if I gave two data points that were close, the output should be at most some big number times how different were the data points. So closeness of data points should relate to the output somehow. That's what I would like to assume from my prediction scheme, okay? And if you assume if this is your setup, you can prove stuff based on a notion called Rademacher complexity. Let me show you the end result. Then I will define that Rademacher after, or maybe next lecture. Let's see. So you can prove the generalization gap for any predictor in your class will be at most 2 times that sensitivity number times whatever that Rademacher complexity is. I can define it to you. Plus some delta divided by your data points. And this will hold with probability at least 1 minus delta. So you get to pick the data. How sure you want to be about your generalization gap estimate? Let's say you want to be 90% and your data is that one. Okay, so pick that. And then you also use some number of data points in your training. This is this part. Okay, and this is a bound on your generalization gap. So this is like related to mostly training process. This is related to how big was your function class. It's again like bias variance type stuff actually. So this part is created by how much wiggling room I have in my prediction scheme. And this part is created by how good it is fitting, okay? But at the end, you can say something theoretical that will give you a bound, okay? And I think Rademacher complexity, I can define it next time. Or maybe I don't define it, doesn't really matter. I'll give you the reference. But at the end, all I'm trying to say is there are some theoretical tools. People have thought about this, but theory does not really capture what we need in practice. But this theory has been developing for a couple of decades now. Okay, that's about it for today. Thank you so much.